So our topic of discussion today is the work energy theorem, right? Something important to take note of is that if you look at most of your past papers, 90% of them you'll see 2 marks for stating the work energy theorem. So I would recommend that you learn the work energy theorem definition in order for you to gain those 2 marks. So even if you don't learn the definition, you can go to the back of your paper, you'll see the formula sheet. If you read the formula out in words, that's the definition of it. So you don't have to memorize it. All you need to do is read a formula, and that's free 2 marks, right? So our work energy theorem states that the net work done on an object is equal to the change in kinetic energy of that object. So let us write this in terms of an equation. So we're already familiar with the first part. We've calculated this countless times. That is net work, which is represented by W net. So the definition states the net work done on an object is equal to, so let us introduce an equal to sign, is equal to the change in kinetic energy. So we know kinetic energy or change in kinetic energy is represented as such. Now, our left-hand side of our equation, which is our work net, is something that we've been doing for the last 2 weeks. Our right-hand side of our equation should be familiar to you. You've done that in, I believe, grade 10 and maybe grade 11. It was part of kinetic energy, calculating velocity, that sort of thing. You did potential energy and mechanical energy as well surrounding that topic. Now, what we now need to do is take the left-hand side, which is what we've already done, and combine it with something that we are familiar with, which is our work energy calculations. So let us now break this up into their separate formulas, and then we'll combine it once again. So I'm breaking it up so that you don't get confused. At any point in time, if you are confused, I would prefer you unmute yourself and speak up, as opposed to typing a message in the chats, as like I said, I don't really have access to the chats while I'm on the whiteboard. It's in a separate window. So let us look at work net. So we are familiar with this. We've done this already. Work net is equal to the sum of all the individual works. So let's say our object has applied force, it has frictional force, it has normal force, and it has gravitational force. So our work would then be the work done by the applied force plus the work done by our frictional force plus the work done by normal force and the work done by gravitational force. Now we can then break those up into their own formulas. So we know that when we are calculating for the work done by applied force, that is just going to be our applied force times our displacement times cos of theta. Work done by frictional force is just going to be frictional force times displacement times cos of theta. Work done by normal force, we can actually exclude that or leave it out because we know that's always going to be 0. This will always be 0 joules. The reason why it is always 0 joules is because our normal force acts perpendicular to the surface on which the object is moving, and our displacement is usually parallel to our surface. So we can conclude that normal force in most cases is perpendicular to displacement. If you have an angle of 90, cos of 90 is going to give you 0. So Always remember that work done by normal force is just going to be 0. So I'm going to exclude that. Now let's have a look at work done by Fg. We can break that up into mass times gravity times displacement times cos of theta. Now that is the work calculations that we are familiar with. Now let's have a look at the right hand side. Let us have a look at how we would calculate or how we would break up our kinetic energy calculations. So we know that a change involves final minus initial. Irrespective of what you're doing, a change is always your final minus your initial. So in this case, because it is a change in kinetic energy, it is going to be your final kinetic energy minus your initial kinetic energy. And kinetic energy is equal to half times our mass times our velocity squared. So this is then going to become a half mass Vf squared minus a half mass Vi squared. Now, as you can see, we have a common factor, which is a half times mass. So we can take out our common factor from this equation, which will then leave us with Vf squared minus Vi squared. Now, we have now simplified the right-hand side and simplified our left-hand side. So let us now combine the two into one. So we can now calculate our work energy theorem using our applied force, if there is, times displacement times cos of theta plus our frictional force times displacement times cos of theta plus our mass times our gravity times displacement times cos of theta, and if there are any other forces involved, which is then equal to a half mass times Vf squared minus Vi squared. So that is basically our work energy theorem. You don't have to remember all of the steps, because it is already things that you know. All we are doing is taking formulas that we are already familiar with, or formulas that are already on our formula sheet in our exam paper, and combining them. So we're just breaking up the formulas as we move along. So we have question 5. A 70 kg box, so that is important, the mass of this object. Because keep in mind, we need mass to calculate kinetic energy, right? So we now have the mass of this object, which is 70 kgs. Is initially at rest. So that is also important. At rest means that this object has a velocity of 0 meters per second, and because they stated initially, that means that that is the initial velocity. At the bottom, okay, so now they've mentioned bottom, so this is our starting point. This is where we are going to start, which most likely means we are going to end at the top of that incline. At the bottom of a rough plane, so this is also important because they've used the word rough. That indicates that there is frictional force, because keep in mind, frictional force only acts when there is a rough surface involved. Inclined at an angle of 30 degrees to the horizontal. The box is pulled up by a means of a light, inextensible string. So because the object is being pulled up by a string, keep in mind, whenever we are dealing with a string or cable, there is tension involved. So this is now going to be our tension force. The box is pulled up the incline by a light, inextensible rope held parallel to the plane. as shown in the diagram below. The force applied to the rope is 700 newtons. So we now know that our tension force has a magnitude of 700 newtons, okay? So all of that information was just obtained by just reading the first paragraph. So it is always important to make sure you read it. If you have to read it twice or 3 times or however many times you have to read it, and if you have to make notes on it, do it so that it can benefit you, okay? So the information that we were able to gain from that paragraph is that this object has a mass of 70 kgs. The initial velocity is 0 meters per second. This object has frictional force. It is inclined at 30 degrees to the horizontal, and there is tensional force of 700 newtons. Okay, so what do we not know? We don't know the magnitude of our kinetic friction. We were not given that. We don't know the magnitude of friction as yet. We also don't know the final velocity. So those are two things that we currently do not know. So let us now have a look at our questions. So our first question, question 5.1, what is the name given to the force in the rope? So we've already discussed this. Whenever we are dealing with a cable, a rope, it is always going to be tensional force or tension. So we can then answer this question. This is going to be tension. Okay. Now, they state, give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. So something important to take note of is that our law or our principle of conservation of mechanical energy states that the initial mechanical energy of a system will be equal to the final mechanical energy of that system when there are no external forces acting on that system. An example of an external force is frictional force. So when we are dealing with frictional force, always keep in mind that you cannot use your mechanical energy, your conservation of mechanical energy formula. As long as friction is involved in the scenario, in the question, do not use your conservation of mechanical energy formula, okay? We'll have a look at, or we'll go through our mechanical energy formula in more detail in next week's class. That is part of our conservative and non-conservative forces that we'll have a look at, okay? Now, our question was, give a reason why the mechanical energy of the system will not be conserved as the box moves up the incline or up the plane. Now, the reason is because we have an external force that is acting on this object. Our external force is frictional force. Because there is frictional force acting on our object, mechanical energy is not conserved. So it is because of frictional force. And how do we know that there is frictional force acting on our system? It is because our question stated that this is a rough inclined plane. So the use of the word rough indicates frictional force. Okay, so let us move on to question 5.3. So after we do 5.3, I'll have a look at the chats to see if there are any questions. So if you do have a question regarding anything that we've done so far, or if a question pops up as I am speaking, you are welcome to type it out in the chats. And when I go to the chats, I will have a look at it. So we have the boxes pulled up over a distance of 4 meters. So this is important, the distance. This indicates displacement. So we now know that our displacement is 4 meters. The kinetic frictional force between the box and the plane is 178.22 meters. So we now have kinetic frictional force. So the only thing that still remains unknown is our final velocity. Okay. So we basically have most of the things that we need to calculate final velocity. So I'm sure one of the next questions would be for us to actually calculate final velocity. So let's have a look at our question. Question 5.3. Draw a labeled free body diagram for the box as it moves up the plane. So we need to draw a labeled free body diagram. Now this is something that a lot of students were struggling with. I believe last week when we had a chat on the WhatsApp group, a lot of students mentioned that they struggle with drawing free body diagrams. So when you are drawing a free body diagram, you start with a dot or a square. That will represent the object that is in question. So I'm going to use a dot. Now that represents my 70 kg object. Now another important thing to take note of is the mark allocation. So we have question 5.3 that is for 4 marks. Because it is for 4 marks, we then know that we need 4 forces. Your mark allocation will give you an idea of how many forces are acting on this object. If you have 3 marks, it's usually 3 forces. If you have 5 marks, it's usually 5 forces. Okay, in this case, we have 4 marks, which means there are 4 forces acting on this object. Now let's quickly list the 4 forces that are acting on this object. So we already discussed there is tensional force or tension. We've identified that there is frictional force or Fk. And we know that because this object is moving on a surface, there is going to be normal force. And this object has mass. Anything that has mass will have gravitational force as well. So these are our 4 forces that we now need to try and show which direction they are acting. So before we even draw our vectors, something that I like to do when I'm dealing with an inclined plane is to draw my incline. So in a dotted line, I am going to draw the inclined plane. This just gives me an idea of the general direction of our forces. So this is my inclined plane. Now let us start with tensional force or tension. We know that tension is parallel to our plane and moving up the incline or moving up the plane. So something important, this direction would represent down the plane and this direction would represent up the plane. So we take our ruler and we put it in the same line as our plane. So you can just line up your ruler with your plane and you can draw your force. So this is our force of tension. And that is represented by a T for tension. So we have now indicated our first force. Let us have a look at the next one. We need to show in which direction is frictional force acting. So we know that frictional force acts in the opposite direction to motion. So because our object is moving up the incline, frictional force will act in the opposite direction, which is down the incline. So down your incline, you can just draw an arrow, and that is going to represent Fk, which is your kinetic frictional force. So we have completed 2 thus far. Let's have a look at normal force. So we know that normal force acts perpendicular to the surface on which our object is moving. So let us now place our ruler perpendicular to our incline, or in other words, you can have it perpendicular to your kinetic friction or your tension for the specific example, because those forces are parallel to your incline. Now that is going to represent our normal force. And finally, let us represent our gravitational force. Now, gravity always acts straight down. So place your ruler 90 degrees to your page, or place your ruler straight in front of you and draw a line. That is going to represent your gravitational force. You do not need to include the components of gravity. You only need the main forces. So we have now indicated all 4 forces, and we'll get 1 mark for each. And if you want to, you can just go and erase this up and down, because that is not needed, nor is this at the bottom. So does anyone have any questions about how we found or how we obtained our free body diagram? Okay, I see there is a question.
Would it be, sorry.
Yes.
Would it be okay if we drew the line for the force of gravity in a parallel form, like not straight downwards, like in a slant with normal force at an incline?
Are you talking about the perpendicular component, like this, for example? Yeah,
like the force. We don't have to indicate whether it's perpendicular. You just write down, yeah, like that, the force of gravity. Would it be fine if we drew it like that?
So you don't, like, for example, you don't want to have this. You only want to have that and call it FG.
Yeah.
No, that would be wrong, because technically that's not FG. Remember, even though it's an incline, gravity is acting straight down. So it's acting in this direction, always, irrespective. So if you state, this states that gravity is acting at an angle, that's wrong. Gravity doesn't act at an angle. If you want
but if we put the perpendicular component,
that would then be correct. Yes, you can do that. So if you, but you first have to show the main gravity. You have to show FG. If you leave it out, you're going to lose 1 mark. So show FG, and then you can put there whether you want to call it FGY or you want to call it FG perpendicular. That's up to you. Then you can also put in the horizontal component, or if you want to call it parallel, whatever you want to call it. You can include those additional components, but you won't get any extra marks for them. But if it helps your understanding, by all means, proceed.
Okay, thanks.
Sure. Okay, so I saw there was a question in the chat. Let me just attend to that quickly. Okay, so someone stated 5.2. If I wrote applied force, am I wrong? What is 5.2? Give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the incline. Okay, so if you wrote applied force, that would be wrong. Keep in mind that there is no applied force acting in this scenario. This question does not have applied force. Even if there was applied force, let's say, for instance, that was intentional force. So hypothetically, let's say that is applied force. Even if it was applied force and you wrote applied force for question 5.2, that would still be marked wrong. The reason is because applied force is not one of the conditions that makes mechanical energy non-conserved, or is not technically considered an external force in a way. Always remember that whenever something is not conserved, always think of frictional force. So why is mechanical energy not conserved? Always remember it is because of frictional force. This statement is actually very important because you'll reach a point whereby you'll need to use certain formulas, right? So one question in work, energy, and power has about, what, 5 ways of calculating it. So you need to be able to choose which way or which method, which formula are you comfortable with using. So you can use your conservation of mechanical energy formula, but if there is friction, you can't. So it negates one of the options that are available to you. So always know the conditions under which you can use each formula. For example, if you want to use your work net equals change in kinetic energy formula, all you need is velocity, mass, and the forces and the forces of each, or the magnitudes of each force. If you want to use your work done by non-conservative forces method, all you need is your heights, which is to calculate potential energy, and you'll need your mass and your velocity to calculate kinetic energy. Because keep in mind that work done by non-conservative forces is equal to your change in mechanical energy. And change in mechanical energy is the combination of your change in kinetic and potential energies. If you want to use the method whereby you calculate using conservation of mechanical energy, you need to make sure that there is no frictional force involved first. So something extremely important, always know what each variable within your formula represents, and always know what formulas can be applied under what conditions. Okay. So to answer that question, for 5.2, if you wrote applied force, that would be considered wrong. The answer is frictional force. The only time that the mechanical conservation of mechanical energy formula cannot be used is when frictional force is present. Okay, so I think that was the last question in the chat. Let us proceed. Okay. So our next question, we have question 5.4. If we want to calculate question 5.4, let us start by reading the question. Question 5.4, calculate the work done on the box by the frictional force over the 4 meters. So this is a nice question. It's nothing too complicated. We're not calculating work net. We're not doing any complicated calculations. It's something that we did in our first work, energy, and power session. All we are doing is calculating the work done by one specific force, which is our frictional force. So we know that our formula is work equals the force times the displacement times cos of theta. Now, because we are calculating the work done by kinetic friction, I'm going to include some subscript so I know that this is work done by kinetic friction. Now, let us discuss what each variable within this formula represents. Our kinetic friction represents the magnitude of our kinetic friction. Keep in mind, or take note of the word magnitude. We are calculating a scalar quantity, which is work. So do not substitute your signs. Don't substitute your directions. Even though force is a vector, because we are using that vector to calculate a scalar, only substitute the magnitude. So if it's a negative sign, because frictional force is moving in the opposite direction to motion, do not substitute a negative frictional force. Only substitute an answer without a sign. That is magnitude. Now our displacement, we were given displacement as 4 meters. and then cos of theta. We'll come back to cos of theta. Let's quickly substitute. So we have work done by kinetic friction is equal to 178.22 newtons times a displacement of 4 meters times cos of an angle. Now, what is that angle? How do we find the angle theta? Keep in mind that our angle theta represents the angle between our displacement vector and our force that we are calculating the work of. So let us go back to our free body diagram and put in our displacement vector so that we can now easily find our theta or our angles. So because the object is moving up the incline, my displacement vector is also going to move up the incline. Now that is displacement. So let us now identify what is the angle between our displacement and our kinetic friction. So if you notice, the angle or the vectors that are formed are basically a straight line. And we know that any straight line is supplementary, meaning that the angles add up to 180. So this is now going to be theta equals 180 degrees. Another way to think about it is both vectors are moving in the opposite direction. That is why they form a straight line. Okay, so this is going to be theta of, let's call it Fk, equals 180 degrees. So we substitute 180 degrees, and we will therefore put this into our calculator. So we put in 178.22 times 4 times cos of 180, and that is going to give us negative 712.88 joules. Why do you have a negative sign? Why is our answer negative? The reason is because energy is being removed from the system. Whenever you end up with a negative work, it is because energy was removed from that object. So 712.88 joules of energy was removed from the 70 kg object as it was displaced through 4 meters. Okay, now a lot of people struggle with the concept of why are we not taking direction? Keep in mind that the formula basically took into consideration direction for you, because cos of theta or cos of 180 is just -1. So that's the same as putting in a negative 178.22. So don't include the magnitude because the formula basically, don't include the direction, the minus or positive sign, because the formula basically does it for you. So why would you want to do the extra work? And if you do include a negative 178.22, your final answer would have been positive. And we know that friction can never add energy to a system. Friction is the force that opposes motion. It's opposing something, so it's removing energy from our system, or from our object rather. So always keep that in mind. Your frictional force must always be negative. If you end up with a positive frictional force, go back and see there's an error somewhere there. Try and fix that error. Okay, so before we move on, I'm going to take my time with the first question, make sure that everyone understands before we proceed. Once we get to question 2, 3, and so on, I'm going to move at a faster pace, and I'm going to look at the chat slightly less so that we can try and get through as much work as possible. So if you have questions regarding what's going on, now's the time to ask so that we can attend to it before we move on to other questions. Keep in mind that I've put this question first because it's one of the easier ones as opposed to the others. Okay, so let us see what's going on in the chats. I can't see. Okay, you've got it. Perfect. Okay. Orabile, you've got your hand up. Do you have a question?
So I would like,
Yes.
why are we using cos 180 instead of the 30-degree angle?
Sorry, you said why are we using cos 180 instead of?
The 30 degrees.
Oh, okay, that is a nice question. Thank you for bringing that up. When you were dealing with Newton's second law of motion, in most cases, your angle represented the angle of the incline, right? But now we are basically dealing with a different topic. Different topic, new rules, new set of doing things, right? So that incline, that 30 degrees, we basically don't need it anymore. Think of it as last year's stuff. That's Newton's second law of motion. Now we're doing new stuff. We're in a new grade, we're in grade 12, we don't need it anymore. But keep in mind, theta is just a representation of any angle. So because you've used theta in grade 11 to represent one thing, don't assume that it's always going to be that thing. It's always going to represent the angle of the incline. You'll see as you proceed with new topics, theta can represent a multitude of things. So keep in mind what each formula, what each variable within that formula represents. The angle theta represents the angle between our displacement vector and our force. It doesn't represent the angle of the incline. So if you look at the two vectors, let me try and redraw this two vectors without all the other forces involved. So this is our object. This is our displacement vector going up the incline, and our kinetic frictional force vector is moving down the incline. Now, if you look at this, it forms a straight line, and there's a 180-degree angle formed because of that straight line. Now that is theta. Does that make sense, Orabile?
Yes, it does. Thank you.
Perfect. Okay, so someone is asking to find angle, you look at the direction of the force. Wait, look at the direction the force is in relation to the displacement. Okay, yes. Sekofatso, when you are calculating theta in work, energy, and power, always look at the force that you are calculating in relation or in reference to displacement. This theta is always from displacement to whatever force you are calculating. So that's what you must look at. You can do what I just did now. You can draw them separately and see what the angles are. If you struggle to do it when there's a lot of vectors on one free body diagram. Always something to take note of is always draw your free body diagram, even if the question does not say draw it. Just always draw it because it helps you with so many things, okay? So always make sure that you draw your free body diagram. There was a hand, I think Fezzi, your hand was up. Do you still have a question or are you sorted now?
Sir, I wanted to ask if we were going to calculate the work done by tension, are we going to use the 30 degrees then?
No, we actually won't use that 30-degree angle. let's do this. Let's scratch that out because we're not going to use it today. It has no importance to our life. Just ignore it. Don't even think about the 30 degrees. If we are calculating tension, right? Do you see that tension is in the same direction as displacement, and it's basically on top of one another? So there's a 0-degree angle between tension and displacement. Something you need to take note of with work, energy, and power, the angles are not given to you in the same sense that your Newton's second law of motion inclined angle was given to you. Your inclined angle was just right there, straight in front of you, you could see it. But now when you're dealing with work, energy, and power, they can't give you the angle because theta has like 4 values in this one question. When you're talking about tension, theta has a value of 0 degrees. When you're talking about normal force, theta has a value of 90 degrees. When you're talking about frictional force, theta has a value of 180 degrees. When you're talking about FG, theta has a value of 120 degrees. Or if you prefer to go anti-clockwise, it'll be 360 minus 120, which will be 240 degrees. So depending on what force you were busy calculating for, your value of theta will differ. So it wouldn't make sense for the person that set the paper or the examiner to give you the value of theta up front, because there's a different theta value for each force, and also because it's an exam. They want to test your knowledge. If they give you the answers up front, what's the point of having an exam? So always keep that in mind. Now, theta is the angle between your displacement vector and your force that you are calculating. So as soon as you start calculating for your work, start by calculating, or not calculating, you don't need to calculate. Start by identifying your angle of theta. This is something that most students struggle with. So if you are having a hard time understanding or keeping up with the theta part, don't stress. There are a lot of students in your position. The whole point of this is for us to learn, improve, and get better. So our first thing is to ask ourselves, what is theta? Theta is the angle between our displacement vector. Now, when I say displacement vector, this is what I'm talking about. This line here with the arrow, this is a vector. This is called your displacement vector. It's also here where I've drawn it in a dotted line. That is your displacement vector. Now, theta is the angle that is formed when your displacement vector and the force are connected. They will subtend an angle. Let's do a few examples quickly on the side. An angle is just produced when two vectors or two line segments are connected, right? That will form an angle. This is an angle over here. Let's call it theta. If you have this two line segments that are connected, this angle here will form theta. So all you need to do is draw two arrows, one to represent displacement, one to represent your force that you are dealing with. Once you do that, you'll be able to identify your angle of theta. In most cases, it's usually 0 degrees, 180 degrees, 90 degrees, or if your force is at a special angle, let's say. So let's say you have this box and it's moving on this flat horizontal surface, and this is our displacement, and there is an applied force at an angle. This angle between your applied force and your displacement vector, that's your theta. Let's say it was 30 degrees. You would now put cos of 30 to calculate applied force. Okay, so keep that in mind. Another thing to take note of is that when the force is moving in the same direction as displacement and is basically on top of displacement or parallel to displacement, there's an angle of 0 degrees. When the force is in the opposite direction to displacement and forms a straight line, the angle theta is 180 degrees. When your force is perpendicular to your displacement, as is the case with normal force all the time, it's going to be 90 degrees. So hopefully that was able to answer your question. And I see there's no messages in the chats, so let us proceed. So we have now calculated the work done by frictional force. How we did that was we substituted the magnitude of our frictional force times our displacement of our object times cos of theta. Now our theta value is the angle between our displacement and our kinetic frictional force. Now all you needed to do was draw your displacement vector moving up the incline, draw your kinetic frictional force vector moving down the incline, and that would have formed a straight line. Thereafter, you would have been able to identify that theta is 180 degrees. Now, let us move on to question 5.5. So question 5.5 states, use the energy principles to calculate the speed of the box the speed of the box after it has moved 4 meters. So this is important, after it has moved 4 meters. So if we are calculating the speed of this object after it has been displaced a total of 4 meters, we are therefore calculating the final velocity of this object. Okay, so there's about 2 ways that you can calculate this. You can use your work energy theorem and state work net equals change in kinetic energy, and you can calculate your final velocity. The second option, which is an option I prefer to use, it's just based on personal preference, you can use whichever option you want to, is to calculate using work done by non-conservative forces. Now, because I have not covered non-conservative forces in our classes as yet, we are only going to do it next week. I am only going to use my work net equals changing kinetic energy formula for all of the calculations today. But if you already know how to use work done by non-conservative forces, I would suggest doing what you like or doing what you're familiar with. If you are using work done by non-conservative forces, you will need to make use of this angle of your incline in order to calculate your height. Because keep in mind, work done by non-conservative forces deals with your potential energy, which deals with height. But we're not going to look at that for today. We are strictly going to look at work net equals changing kinetic energy. So let us start with our formula. That's the most important place. We start with our formula, and keep in mind this is 5 marks. So make sure you understand how to do this, because these types of questions always pop up and they're always between 5 to 7 marks within a work energy question. So this is important. If you can do that, you basically understand everything else. So work net equals change in kinetic energy. Now, to make life easier and to make it easier to understand, I'm going to break up my calculations. I'm not going to calculate for everything all in one equation. I want you guys to get used to the process, so I'm going to break it up. Maybe as we move through the session and I feel like you guys should be okay with it, I'll start to do everything within one equation. But for now, to make it easier, let us break it up. So we are going to start with calculating work net first. Let us first calculate work net. Now we know that work net is the sum of all our individual forces. So we need to calculate the work done by tension force, the work done by frictional force, the work done by normal force, and the work done by gravitational force. So work net is equal to the work done by our tensional force plus the work done by Fk plus the work done by normal force plus the work done by Fg. So let us now go and individually calculate those four works. So I'm going to move this a bit down so that we can start with our work calculations. Actually, let's leave it up there. We'll just do the calculations underneath. So work done by tensional force, right? So our formula is still the same. Work equals, or work done by tensional force is equal to our tensional force times our displacement times cos of theta. Now, what is our tensional force? The magnitude of our tensional force was given to us previously. Let us go and have a look at what that was. So we can see the tensional force is 700 newtons. So let us substitute 700 newtons times our displacement, which is 4 meters, times cos of theta. Now let us go and have a look at our free body diagram and have a look at what is our value of theta for tensional force. So like I mentioned previously, if the force is moving in the same direction as displacement and it is parallel to displacement and it's on top of one another, as you can see there, the angle between it is going to be 0 degrees. So our angle theta of tension is 0 degrees. So we are now going to substitute 0 degrees within our formula, and that is then going to give us, let's just have a quick look on our calculator, 700 times 4 times cos of 0, and that is going to give us 2,800 joules. I can see that there is a few questions in the chat, so I'll have a look at that in a moment. Let us first quickly go through how to calculate for work net, and then we'll attend to the chats. Now, we already calculated the work done by kinetic friction, which was negative, I think it was, let's see, where is that? Oh, there's it. Negative 712,88 joules. Work done by normal force is just going to be 0 joules because our normal force is perpendicular to our displacement and cos of 90 equals 0. Now, the important part that I want us to have a look at in this example is the work done by Fg, the work done by gravitational force. Now, in our last two classes, I used the method whereby I included my inclined angle in order for us to calculate the angle of theta of Fg. But a lot of students found that difficult. So I'm going to use a new method today that I feel might be slightly easier, and it is something that you should already be familiar with. So there was a question previously when we started the session, why don't we include the components of Fg? So now that I'm going to calculate for the work done by Fg, I'm not going to use the force Fg itself. I'm actually going to use the components of Fg. So I'm going to just indicate that here. I'm going to use the components of Fg. That is going to be my work done by Fg. So let us start by including our components into our free body diagram. So let's start with our perpendicular component, also known as Fgy. So that is going to be in the same direction as normal force, and that is Fgy or Fg perpendicular, whichever you prefer to call it. Now, we have one more component, which is Fgx or Fg parallel. Now, that component is usually drawn like this. But now, I don't want to have it just floating down there. I want to have it so that it is connected to my dot, so that I can try and form an angle between displacement and my parallel component. So all I'm going to do is move that component slightly up so that it is connected to my object. Doing this doesn't change anything. It's just a different representation of the exact same thing. So we have Fg. Hopefully you are able to see that, and that is Fgx, my parallel component. So I'm now going to calculate the work done by Fgx and Fgy. So something important, even before we start, you don't actually have to include Fgy because it's always going to be 0. Because keep in mind, our angle between normal force and displacement is 90. And normal force and Fgy always form a straight line. Angles on a straight line, 90 plus another angle gives you 180. That means that this is also 90. So because the angle of theta of Fgy is 90 degrees, that means that the work done by Fgy is going to be 0. So if you want to, if you feel confident, if you feel happy enough to leave it out, by all means proceed. So I am now going to calculate the work done by Fgx, which is the component of our gravitational force that acts down the slope. So work done by Fgx is going to be equal to the force of Fgx times displacement times cos of theta. Now, let us have a look at what our formula to calculate the force of Fgx is going to be. So based on what we already know from Newton's second law of motion, this angle over here is the same angle as our incline, that is 30 degrees. Now, our Fgx is normally drawn here, so let's just call that x. Now, we can see that the position of Fgx relative to our 30-degree angle is opposite. So we are going to use sine, because sine is the only trig identity that makes use of opposite in the specific scenario. Because keep in mind, when we're dealing with Newton's second law of motion, or when we're dealing with forces on an inclined plane, we make use of two identities, sine and cos. So between sine and cos, which one makes use of opposite? It's sine. If you wanted to calculate Fgy, you would use cos, because the position of the y vector is adjacent to that 30-degree angle. Okay, so let us just put this in. So we know that Fgx is equal to Fg, which is mass times gravity, times sine of 30 degrees in this case. Okay, it's not always 30 degrees, it's just whatever angle the incline is. So let's sub that in. So this is going to be mass times gravity times sine of 30 degrees times displacement times cos of theta. Now let us substitute those values. What is our mass? Our mass is 70 kgs. So we are going to have 70 times G is 9,8 times sine of 30 degrees times a displacement of 4 meters times cos of an angle. Now, let us go back and look or try to identify what is our angle. So we can see that FGX is moving in the same or moving on is basically on top of FK, right? So it's going to have the same angle. So our angle theta of FGX is going to be the same as our kinetic friction because it's moving in the same direction. So there's going to be the same angle between displacement and FGX. So that is 180 degrees. Now we can put this onto our calculator. I know it's quite a long one as opposed to the previous ones. So let's see. So we have 70 times 9.8 times sine of 30 degrees times 4 times cos of 180 degrees. And that gives us negative 1,372 joules. Now, I'm going to stop there for a moment. I want us to just have a look or just check if there are any questions, because I know that this is sometimes a tricky force to calculate with, and this looks slightly confusing because of the sine and the cos. Let's do this. This whole part that I'm highlighting in yellow, that represents the force Fg. Okay, maybe that should make things a bit easier. So if you have any questions related to what we've just done so far, please unmute yourself and speak up, or you can raise your hand if you're typing out a message in the chats. Whatever it is that you want to do, you are welcome to ask what you need to ask. Okay, so it seems like the chats are empty actually. So okay, no, someone has a question. So why is it sine? Okay, so it is sine because the position of FGX relative to the angle of 30 degrees is opposite. So if we were to, let me redraw this slightly bigger. So if this is your triangle, and if you look at the angle 30 degrees, you can see that FGX is opposite that 30 degrees. And what identity between sine and cos uses opposite? It is FGX. Sorry, what am I saying? What identity uses opposite between sine and cos? It is sine. So because the force is opposite the angle of 30 degrees, you use sine, not cos. Okay, that sine is only to calculate the magnitude of the force. That sine is not from the cos of theta from the work energy formula. Please keep that in mind. Okay, does anyone have any other questions? let's do this. How many people understand what's going on? Just indicate with a thumbs up. Okay, so it seems most people are okay. So then let us proceed. Let me pick up the pace as well. Then we can get through more stuff. Okay, so let's continue. So we have now calculated the work done by each individual force. So what we are now going to do is we are going to add up all of the forces, all of the works, and find our work net. So we're going to say 2,800 minus 712.88 minus 1,372, and that is going to give me a work net of 715,12 joules. So that is my work net. That is what I needed to solve part of this question. Okay, now let us have a look at how we would solve the right-hand side of that equation. So let's have a look at how we are going to find the change in kinetic energy. So we know that change in kinetic energy is equal to a half mass into Vf squared minus Vi squared. Keep in mind, this is what we are solving for, okay? Which is our final velocity. I know it's been quite a while since we read the question, so let's go back and read the question to refresh your memory. So our question is, use energy principles to calculate the speed of the box after it has moved 4 meters. So we are calculating for final velocity. Okay, so let's do that. Let's see. A half times our mass. Our mass was 70 kgs times Vf squared is going to remain that since it's unknown, time minus 0 squared. Now, if you are wondering where did the 0 come from, it came from the question. We were given, or we were told, that this object was initially at rest at the bottom of the incline. So one of the very first things that we actually identified. So it states a 70 kg box is initially at rest, meaning that it is initially stationary. It's not doing anything, it's just chilling there, it's stopped. So we know that there is an initial velocity of 0 meters per second. So let us simplify this equation. A half times 70 is just 35. Vf squared minus 0 squared is just Vf squared. So that is our change in kinetic energy. Wasn't so bad, right? All we needed to do was substitute mass and the velocities that we were given if we had them. Okay. Just give me a moment, please. Okay, sorry about that. Where were we? Okay, so we have now calculated the work net and we have calculated changing kinetic energy separately. Our formula has them together, so let us take both the left-hand side that we calculated and the right-hand side and combine them into one formula. If you feel confident and you feel like you understand this, you know what's going on, you're more than welcome to do both parts in one formula simultaneously. Okay, so our formula is work net is equal to change in kinetic energy. Now we've calculated our work net as 715 12 joules, and we've calculated our change in kinetic energy as 35 VF squared. Okay, so now, as you can see, this equation looks so much easier to deal with now. It's simplified. It's quite nice to work with. So all we are going to do is solve for VF from this equation. So we can divide both sides by 35. And that is then going to give us VF squared equals, let's see, divide this by 35. That is going to give us 20,432. We can square root both sides to get rid of the squared, and that is then going to give us a velocity of, or rather final velocity of, let's see, 4,52 meters per second. So that is our final velocity for this particular question. So I'm going to zoom out so you can see the entire question. If you have any questions, any parts that you are unclear of, anywhere that you are stuck, ask now before we move on to the next question. Okay, so is everyone okay then? No one has any questions? Everyone's fine? If you need something to be repeated, put your hand up. Okay, then okay, wait, now I see some questions coming in. Okay. How did you get 715.12 as W net? Okay, so Sehofatso, we calculated work net by adding up all the individual works. So that 715 came from adding up positive 2,800, came from adding up negative 712.88, and it also came from adding up 0, and it also came from adding up this negative 1,372. So all I did was I added up all those individual works, and that gave me my net work. Okay. Let's see. Anyone else with a question? Okay, so let us proceed then. So our last question of this paper, when the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide down to the bottom of the inclined plane. So basically what has now happened is that this object that was moving up the inclined plane, once it reached that 4-meter point up the inclined plane, the rope snapped, it broke. So there was no force that was pulling it up the incline anymore. And because of frictional force and because of the parallel component of Fg that pulls the box down the slope, the box then started to slide back down the slope. Okay, so our question is, what will the total work done by friction when the box moves up and then down to the bottom of the incline? Okay, let's read that one more time. What will the total work done by friction? Okay, so we now need to calculate we now need to calculate the work done by friction, right? So let us just put this in. Let's highlight this. So the total work done by friction. So don't confuse this with the previous work that don't confuse this with the previous frictional force that we calculated, right? That previous frictional force that we calculated was when there was a tensional force moving up the incline as well. But in this specific case, they want us to find what is the frictional force, or what is the work done by frictional force after the rope has snapped, or after the rope has broken, so that the object now starts to move down the incline. Okay, so let us quickly draw a quick visual representation of that so that you can understand. This is going to be 5.5. So we have this incline, right? And at a certain point, this rope snapped. So now there is no longer going to be a tensional force involved. So we still have Fg moving down the incline. We still have normal force acting perpendicular to the surface on which the object is moving. And now, because our object is moving down the incline, our frictional force is no longer acting down the incline, because keep in mind, frictional force acts in the opposite direction to motion. So because our object is moving down the incline, frictional force is now acting up the incline. And keep in mind, we have the components of Fg. So we have Fgx and Fgy that are acting. And because our object is moving down the incline, our displacement is going to be down the incline. So this is basically what is now going on. Because the rope snapped, the object now moves down the incline. Think of it as though if you were in an elevator, if you're in a lift, and for whatever reason, the rope in that lift snaps while the lift is going up. Maybe it's going from floor 1 to floor 2, and now the rope snaps. So that lift is no longer going to continue to go up because the rope has snapped. It is now going to fall down towards the ground. So just as in this case, the rope that was pulling this object up the incline has now snapped, it's broken. So this object, instead of now continuing to move up the incline, it is now going to proceed down the incline, which means because our rope snapped, there will no longer be tensional force, and our frictional force and our displacement will move in opposite directions. Okay. Yeah, so let us go back and quickly check. What was our question again? I forgot. When the box is 4 meters up the incline, the rope accidentally breaks, causing this box to slide down to the bottom of the inclined plane. What will the total work done by friction when the box moves up and then down to the bottom of the plane be? Okay, so we now need to calculate what is the work done by frictional force going to be. So let's have a look. Keep in mind, we're calculating, let me see, did they say the frictional force itself or work? Sorry. What will we're calculating the work done by frictional force. Okay, so let's see. Something important to take note of is that tension is missing from my diagram because the rope snapped, so there will no longer be tension involved. Okay, so if we have a look at this, let's see, our work done by frictional force is actually going to be double our previous answer because tension is now removed. So our work done by the new frictional force is equal to twice the work done by the old frictional force. So this is the new one. This would be the old one. That is then going to be work done by Fk is then equal to 2 times our previous frictional force. What was it? 712.88. So where did that go? Oh, here's it. So this is now going to be negative 712.88 joules. We can put this onto our calculator. Just give me a moment. Two times 712.88, that's going to give us negative 1425.76 joules. Okay, so that is basically the 1 mark question. There wasn't much calculation involved. All we needed to identify was, because tensional force was removed, because there was no longer a force that was pulling this object up the incline, because that tensional force has been removed from our system now, our object is going to slide down the incline, and the frictional force is going to be twice, or rather the work done by frictional force is going to be twice that of the previous frictional force. Okay. So let us zoom out quickly, take a few seconds to see if anyone has any questions before we proceed. So let me quickly check the chats. Okay, someone is asking, how did I get 715.12 as work? Oh no, I attended to that already. Is it compulsory to put the square root? No, it's not compulsory to put the square root. I only put the square root so that when I take a screenshot and students go back to have a look at the solutions, they know that you need to square root that. But if your question is, do we not need to put the square root because you want to leave your answer as VF squared, then that is incorrect. Don't leave your answer as VF squared. Make sure that you solve for final velocity, not final velocity squared. There's a difference. Always square root if it's squared, okay? Okay, then there's a hand that's up. Rethabile, you have your hand up. What's your question?
No, sir. I figured it out. It's fine.
Okay, cool. So we have question 5, a crate of mass 70 kg, so that's important. The mass slides down a rough inclined plane, so that is important. It indicates the presence of kinetic friction or frictional force, whichever you want to call it. Because there's frictional force involved, we cannot use our conservation of mechanical energy principles. Keep that in mind. Makes an angle of 20 degrees with the horizontal. So keep in mind, we don't really need this right now. So don't pay attention to that. With the horizontal, as shown in the diagram below, the crate experiences a constant frictional force of 190 newtons. So we now know that our frictional force is 190 newtons. Let's see. The force acting on the crates. The force acting on the crate are represented by R, S, and T. So used S and T to represent the forces that are acting on this object, okay? So they haven't really told us what it is, but if you have a look at that, you can already see what it is. Let's do something interesting. What do you guys think force R and S is? You can type your message out in the chats, or you can unmute yourself and speak up. What do you think force R and S is. Priyanka, you mentioned you cannot see the questions. Have you just entered the class now, or have you been here the whole time and then all of a sudden you just couldn't see it? Yes, Mapula. S is in fact, yeah, S is in fact gravitational force. Mapula, Cindy, you guys are correct. Okay, sharp, perfect, Priyanka. Okay, so Cindy, that is correct. S is Fg. Mapula, you said T is tensional force. Okay, yeah, if there is a string, we haven't really gone to see that. I'll double check. Actually, they said a crate of mass slides down. This thing is sliding down. Okay, no, Mapula, tensional, no, sorry, not, yeah, Mapula, T won't represent tensional force. I'll explain in a moment. Lethabo, R is normal force, S is weight, perfect, R, Mapula, R is normal force, yeah, perfect. So you guys seem to have an understanding of what's going on. The only one that seems to have been a bit confusing is T. Please do not see T and automatically assume tensional force. The T just represents any variable. They could have used A, B, C, X, Y, Z, anything. That T is not tensional force because the question did not make use, or the question did not mention any rope or string. Only when the question mentions a rope or string is there tensional force. Now, they've mentioned that this object is moving down the incline, it's moving down the plane. So our motion is down the incline. Whenever the object is moving down the incline, there's always a force that acts up the incline, known as frictional force. Yeah, so this T represents frictional force. This S represents Fg, and this R represents normal force. So that is the forces that are acting on this object. So T does not represent tension, it represents frictional force, okay? And that would have given us our 3 marks. Then it states, give a reason why force R does not work on the crate. So our question is, why is force R not working on our crate? So it goes back to what we mentioned in our first session 2 weeks back. Why do we have 0 work? We have 0 work because the angle between our force and displacement are 90 degrees. So the reason, or the answer to 5.2 is because normal force is perpendicular to displacement, therefore cos 90 equals 0. Or if you want to, you can just say that the force, or you can say normal force, is to displacement. That is why we will end up with 0 work by normal force. So let me quickly include my displacement in here. This is going to be displacement. Something else that's important to take note of is that there's going to be Fgy and Fgx also acting. Keep in mind that Fgx is the force that is pulling this object down the slope. That is why the object slides down. It is due to Fgx, okay? Now, the crate passes point A at a speed of 2 meters per second and moves a distance of 12 meters before reaching point B lower down on the incline. Calculate the net work done on the crate during its motion from point A to point B. So because we are only taking into consideration point A and point B, I'm going to take point A as my initial, and I'm going to take point B as my final. That then means that my displacement is 12 meters, and my initial velocity will be the velocity at point A, which is 2 meters per second. Are we given the velocity at point B? Let us see. The crate passes point A at a speed of 2 meters per second and moves a distance of 12 meters before reaching point B lower down on the incline. Okay, so we were not given the final velocity, or you can think of it as velocity at point B. We were not given that value. So our question 5.3, calculate the net work done on the crate during its motion from point A to point B. So we need to calculate the net work on this crate. I'll have a look at the chats after question 5.2. If you do have a message in the chats, I'll attend to it at after 5.3, sorry. So this is question 5.3. Let us start with drawing our free body diagram. So I'm going to include my incline, just helps me to draw my free body diagram. Okay, so that is my incline or ramp or whatever you want to call it. Now, we know that there are 3 main forces acting on this object. That is kinetic friction, normal force, and Fg. Now, Fg also breaks up into 2 components, which are Fgx and Fgy. So basically, I need to draw 5 forces on this diagram. So let's start with our kinetic friction. Kinetic friction is acting up the incline because the object is moving down the incline. Always keep in mind that whenever always keep in mind that kinetic friction acts in the opposite direction to the motion of the object. Okay. So that's our first force. Let us now put in our normal force. Normal force always acts perpendicular to the surface on which the object is acting. So it's going to be perpendicular to kinetic friction and to the slope. So that is going to represent our normal force. Now, let us draw our force Fg. So I'm going to start by drawing the 3 main forces that are acting on here, and we'll draw the components in last. Fg always acts 90 degrees down. So that is our force Fg. Okay, now before I do my components, I'm actually going to put in my displacement vector, so it makes it easy for us to identify our angles theta. If you have a question, I would suggest typing it in the chats as soon as you have your question or as soon as you think of it. That way you don't forget it. Okay, if you are going to ask at the end. This is displacement. Let me not use an arrow. I don't like using an arrow for displacement. This is actually supposed to be a dotted line. So that is our displacement vector. Now, let us now include our FG parallel and FG perpendicular. So FG perpendicular is going to act in the same or along the same plane as normal force, but in the opposite direction. So you can place your ruler along the straight or along your force vector and have it act straight down, or not straight down, but straight down within that plane. So that is going to be FGY. Now let's have a look at FGX. Now, just as before, I'm going to put it as a force coming out of my object as opposed to having it down there by FGY. It doesn't change the force, nothing is different, it's the exact same thing, because we already know that FGX is parallel to the surface. So this is going to be my FGY, sorry, FGX, I mean. So that is the force FGX. So we've now drawn a free body diagram in which we have included all of our forces as well as our displacement vector, which is going to help us to calculate theta. All of that extra work is just to make sure that our theta values are correct. So let us start. In order for us to calculate work net, we need to first calculate the work done by each individual force. So the work done by kinetic friction, the work done by FGX, the work done by normal force, and the work done by FGY. Okay, so we basically need to calculate the work done by all, let's see, 1, 2, 3, 4, the work done by all 4 of those forces, and then add them up, and that is then going to give us the net work done. So let us start with FK, the work done by our kinetic friction. So we know that our formula is going to be FK times displacement times cos of theta. Now, FK has a magnitude of 190 newtons that was given to us in the question, times displacement. What was our displacement? Oh, our displacement was 12 meters. It was given to us here in the question, times cos of theta. Now, what is theta? Let us go and have a look at how do we calculate for theta in this particular case. And I kind of like this question. Reason being is because we previously did a question whereby the object moved up the incline. Now, it's kind of nice or refreshing to see an opposite approach whereby our object is moving down the incline. So let's see. If we have a look at from our displacement vector until the force or until the vector of Fk, we can see that theta of Fk is equal to 180 newtons, because they are along the same line but moving in opposite directions, which means that an angle, or rather a straight line, is created whereby an angle of 180 degrees is subtended. So our value of theta is 180 degrees, and if we put that onto our calculator, let's see, 190 times 12 times cos of 180, and that is going to give us negative 2,280 joules. Now, let us have a look at the work done by FGX. So we previously discussed that FGX, the formula of FGX can be calculated as mg sine of the incline angle. In this case, let us go and have a look at what that angle is. It is 20 degrees. Okay, now that is how we are going to calculate FGX. So that is our formula for FGX, mg sine 20 degrees times displacement times cos of theta. Now let's substitute. What is our mass of our object? Our object has a mass of 70 kgs. So it's going to be 70 times g, which is 9,8, times sine of 20 times displacement of 12 meters times cos of 0 degrees. Now let's have a look at how did I end up at 0 degrees. So in this case, FGX is similar to tension in terms of theta as our previous question. So you can see that FGX and our displacement vector are moving in the same direction and are basically on top of one another. So there isn't any space between them. So our theta of FGX is equal to 0 degrees. So if you notice, in our previous FGX theta example, it was 180 degrees. So this is quite a nice visual of why we should not memorize angles of theta. Always understand how to obtain it. Don't memorize it, because they are different in different scenarios. So let us put this onto our calculator. 70 times 9.8 times sine of 20 times 12 times cos of 0, and that is then going to give us positive 2,815,51 joules. Okay, so we have now calculated for the work done by kinetic friction and the work done by our parallel component of Fg. Now let's have a look at the next two. So for the sake of space, I'm actually going to erase them and just verbally discuss the answers. So work done by Fgy is the same as the work done by normal force, which is 0 newtons. And the reason behind that is because those forces, let's just say force, is perpendicular to displacement. So whenever your force is perpendicular to displacement, it's always going to produce a 0 work. As you can see, our displacement is here, and there's a 90-degree angle between our displacement and Fgy. And there's also a 90-degree angle between normal force and displacement. That is why we have 0 work done by both those forces. Now let us calculate the net work. Our net work is going to be equal to negative 2,280 plus 2,815,51 plus 0 plus 0. But we don't need to include that because 0 is nothing, so it doesn't really have any effect. All we are doing to calculate net work is to add up the individual works. So put that onto your calculator and you should end up with a net work as 535,51 joules. Now that is our net work. So how did we find that network? Our first task was to draw a free body diagram so that we are able to easily identify the forces that are acting on the object as well as our angles of theta. We then calculated the work done by frictional force, the work done by Fgx, and added them up to get the net work. Okay. So a quick recap on theta. If you look at Fk and our displacement, Fk's vector is moving up the incline, whereas our displacement vector is moving down the incline. And they form a straight line in opposite directions. Therefore, they are creating a straight line. And a straight line is supplementary, meaning it has an angle of 180. Now, if you look at Fgx and displacement, both are moving in the same direction and are basically on top of one another. So there's an angle of 0 degrees between them. Okay. So give me a moment to go through the chats quickly to see if there are any questions. Okay, so there are a few. Okay, so, okay, that's fine, that's fine. Okay, so we have 5.2. What if I said not on the path of motion? Okay, Cindy, just give me a moment to try and understand what you're saying. 5.2, give a reason why R does not work on the crate. 5.2, what if I said not on the path of motion? Okay, Cindy, technically that answer is incorrect. The reason why that answer is incorrect is because not being on the path of motion does not guarantee that that the work will be 0. Because keep in mind that frictional force is never in the path of motion. Frictional force is always in the opposite direction to motion, but that produces a negative work. Okay. And you can also have forces that are at angles to displacement or at angles to motion. Those are not in the path of motion, but they will produce either a positive or negative work depending on the angle. So I would recommend that you use the phrase, the force is perpendicular to displacement for 5.2. That is the whole reason that work is 0. Work is only 0 if the force is perpendicular to displacement. Or you can say if the angle between the force and the displacement is 90 degrees. That is also acceptable. Okay. Okay, so there's another question. So is it a must to use a small letter n to represent normal force? No, it is not a must to use a small letter n. You can represent it as capital N or you can represent it as Fn. It does not matter. I just personally like to use a small n. You can use whatever you want. It's up to you, as long as you understand what that means. Okay. Why is displacement going down and not up this time? Okay, so Mallory, displacement is going down because the object is moving down. Displacement is dependent on the direction of motion. So if the object goes up the incline, displacement is going to be up the incline. If your object is going down the incline, displacement is going to be down the incline. Okay, so displacement is basically the direction of your motion, and always remember that frictional force is in the opposite direction to motion. Okay, so if the object is going up the incline, friction will act down the incline. If the object is going down the incline, friction will act up the incline, okay? So friction is opposite to displacement and opposite to motion. Displacement is in the same direction as motion, okay? Okay. So before we proceed, those are only the chats. Is there anyone that wants to unmute themselves and ask a question, or anyone that still has a question? You are more than welcome to ask now before we proceed. Okay, seems like everyone seems to be okay, so let us proceed. Now, our next question, write down the work energy theorem. So as you can see, this is an easy 2-mark question. All we need to do is write down the work energy theorem. If you don't remember the work energy theorem, go to the back of your question paper, read your formula in your mind. Don't read it out loud because it's a test, you'll get into trouble. So read it in your mind. If you read that formula, work net equals change in kinetic energy. Let's rephrase it slightly. The net work of an object is equal to the change in kinetic energy of that object. So all we needed to do was read the formula and add object. So hopefully, even if you don't remember it, you can just go to the back of your formula sheet and in your mind read out the formula. Even if you don't include object, if you just say the network equals a change in kinetic energy, you'll still get your marks. Okay. Okay, someone is asking, why is displacement going down and not upwards this time? Oh, okay, no, never mind. I read that already. Never mind, that question was answered. Okay, so that is question 5.4. No calculation necessary. It's just a simple definition of a law, and let us proceed. Okay, so question 5.5. Use the work energy theorem to calculate the speed of the crate at B. So now we need to calculate the final velocity, which is the velocity at point B. Something quite nice about this question is that we have already calculated work net. So all we now need to do is calculate change in kinetic energy. So let us actually go and do that. Okay, this is question 5.5. We need to calculate the final velocity, or the velocity at point B. So our formula is work net is equal to the change in kinetic energy. Now, we have already calculated work net in a previous question, so all we now need to do is substitute work net. We will not be penalized for any marks. We'll receive the full marks because we've already calculated it. You don't need to recalculate it. And we know changing kinetic energy is a half mass times Vf squared minus Vi squared. Now, bring down 535,51 equals a half times our mass. Our mass is 70 kgs times our Vf squared is what we are calculating minus V initial. Let us go back to the information from the question and find out what is our initial value, or our initial velocity. Let us see. Okay, there it is. Our initial velocity is given as 2 meters per second as per the question. So all we need to now do is substitute 2 meters per second And don't forget to put the squared. If you only go and put 2 and forget the squared, you're going to end up with a wrong answer, because keep in mind the velocities are squared in this formula, okay? Now, from here we can multiply a half times 70, which is going to give us 35, into VF squared minus 4, because 2 squared is 4. From this point, we can divide both sides by 35, divide by 35, and that is then going to give us, just give me a moment, divide by 35, and that gives me 15.3. So this is 15,3 equals VF squared minus 4. From here, we can take 4 to the other side. So it's going to become 15,3 plus 4, which is going to be equal to VF squared. So let's just quickly erase this and add it up. That's going to be 19.30. From here, we can square root both sides, and we can therefore conclude that our final velocity, or the velocity at point B, is going to be, let's see, wait, what did I do? Just give me a second. Square root of 19.3, that gives me 4,39 meters per second. So we have now calculated our velocity at point B, or you do it as your final velocity, by using our work energy theorem. So what did we actually do? We already knew what our net work was. So all we did was we substituted the net work from our previous question into our formula. We then substituted the mass of our object as well as the initial velocity, because both were known. From that point, all we did was solve for the unknown, which is our velocity at point B, also known as our final velocity. And that is the last question for that.